Hey everyone, I wanted to take a few minutes to go over your semester end project. So let's take a look at our chemistry neutralization project. So of course, if after this video you're still confused, obviously reach out. We'll get you the help that you need so that we can get this project turned in. But I'm going to walk through it and hopefully address any questions that might come up. So as always, we'll read through it. You can, of course, fast forward through this if you don't want to hear me read it, but I'm going to go through each section and talk a little bit about what's kind of going on here. So the purpose is to determine the amount of sodium bicarbonate or baking soda necessary to correctly neutralize 100 milliliters of acetic acid or vinegar. So essentially we're taking this age-old middle school vinegar baking soda volcano type thing, and we're using it to figure out how can we get exactly a pH of 7. How can we neutralize the acid and the base by mixing them together? So let's read through the introduction and we'll pause and talk a little bit about what's being said here. So a neutralization reaction is when an acid and a base react to form water and a salt. It involves a combination of hydrogen ions from the acid and hydroxide ions from the base to generate water. The neutralization of an acid and a base has a pH equal to 7. When a solution is neutralized, not only will water be formed, but also salt. A chemical salt is formed from the anion of an acid and the cation of the base. For example, when you mix hydrochloric acid and sodium hydroxide, you get the following chemical reaction. HCl, or hydrochloric acid, plus NaOH, or sodium hydroxide, react to form NaCl, or sodium chloride, and H2O, or water. The H from the HCl combines with the OH from the NaOH to form water. The Na from the NaOH combines with the Cl from the HCl to form NaCl, which is our salt we refer to as table salt. Thus, if you mix a very dangerous and toxic acid with a very dangerous and toxic base in perfectly equal amounts, you'll end up with safe, drinkable salt water. So let's take a look at what it looks like when we mix all of those letters together. So on the left here we can see our acid. So HCl is hydrochloric acid, and by itself it is dangerous, it is toxic. On the right we can see NaOH, and it's our base. Again, by itself it's basic, it's toxic. When we look at our solutions, remember our solution is a mixture of a solute. In this case our solute is HCl and water. And when we did our project where we created a solution, we talked about how that ionic compound breaks apart. So in water, we can see that ionic compound HCl breaks apart into the H cations and the Cl anions. Well, something similar happens with the base. So if we look over on the right, we can see the base is another ionic compound dissolved in water. Right? It's a solution, and its solute breaks apart into our Na plus, or our sodium cations, and our OH minus, or our hydroxide anions. And together, when we pour them in the same container, something special happens. We form water and a salt, and let's see how that happens. Well, we can see the Cl's from our acid and the Na's from our base are going to come together to form that NaCl, that table salt. Well, what's going to be left is our hydrogens from our acid and our hydroxides from our base, and when we put them together in perfectly equal amounts, all we have in our new container is water and salt. So this is what we're talking about if it's mixed in perfect amounts. If it's not in perfect amounts, if it's just one extra H or one extra hydroxide, it's going to result in an acidic or a basic solution. So let's say, for instance, we put one extra hydrogen ion. Well, it doesn't have an OH to connect to, so it's not going to form water, but instead it will become acidic. On the opposite end of the spectrum, if we do the same thing with the hydroxide, it would remain basic. So our goal is to make sure when we're mixing our vinegar and our baking soda that we're getting the same amount of protons being donated by the acid as we are protons being accepted by the base. So that's kind of what's going on when we're looking through the introduction in terms of pictures. That introduction will also help us to address the pre-lab questions. So for example, question number 1 asks, what is a neutralization reaction? Well, again, if we look up at the introduction, this very first sentence answers our question. So I'm not going to go through and address all the pre-lab questions. Again, if you have something specific that you need help with, reach out. But the pre-lab questions can be addressed by reading through that introduction. So let's go ahead and let's skip forward to our second page, which starts with a prediction. So don't skip this step. So how much baking soda, the base that we're using, do you think it will take to completely neutralize 100 milliliters of vinegar, your acid, and how did we arrive at that prediction? So first off, I would recommend that you make your prediction in teaspoons. So 1 teaspoon, 2 teaspoons, a half a teaspoon, whatever you think, right? Talk about how many, and don't forget to address the why. Why did you pick 1 teaspoon? Why did you pick 2 teaspoons? Whatever you picked, justify why you made that prediction. Once we've created our prediction, we can go ahead and we can work through the procedure. So again, I'm going to look through these steps. I'm going to try to explain them through drawings, and if there are questions, reach out. But number 1 suggests that we start by measuring out 100 milliliters of acetic acid, also known as vinegar, in your 100 milliliter graduated cylinder. So let's take a look at what that would look like. Well, remember, of course, your graduated cylinder is that big giant plastic tube with all of those tick marks, and remember, those tick marks are called graduations. So you're going to take your vinegar, you're going to fill this up to as close to 100 milliliters as you can, and then we're going to record the actual amount in our data table. So for trial 1, let's say we tried to measure out 100 milliliters and we only got 99. We're going to put 99 milliliters in the table. If you got 101, that's fine. We just want to make sure that we are recording the exact volume in our data table. So I've measured out 99. I'm going to record 99 milliliters. The second step is we are going to then take this vinegar and pour it into any kind of baking dish. This could be a cereal bowl. It doesn't matter. We just want to get it out of that graduated cylinder. So we're going to take that 100 milliliters, 99 milliliters, whatever you've measured out. We're going to dump it into a new container, and then we are going to take those pH strips that you guys got in your lab kit. We're going to stick it in that solution, and we are going to record the pH that we see. So if you see red, you're going to record it to the corresponding value. If you see orange, you're going to record the corresponding value. So I'm, of course, working hypothetically here. Let's say I go through this and I record my pH to be somewhere between 2 and 3. So I'm estimating it to be 2.5. Again, I'm going to record this value in my data table for trial 1. Once we have our vinegar in our bowl, once we have our pH taken, what we are going to do is we are going to measure out the estimated, the predicted amount of teaspoons. Remember, back up here, we've predicted a number of teaspoons. We're going to measure that out, and we are going to record what we've measured out in our data table. So, again, arbitrarily speaking, let's just say I measure out 1 teaspoon. So I'm going to grab my box of baking soda. I'm going to put it into my teaspoon, and I'm going to wait. All right. So my next step, right? Number 5 is done. Number 4 is done. Number 6 now, once we've mixed the two together, we then need to record our final pH. So we are going to take our baking soda. We are going to mix it in with our vinegar. We are going to wait for that reaction to happen, to end, and then we are going to measure the pH again. Once I measure the pH again, I am going to then record it into my data table. Remember, I am shooting for a pH of 7, okay? Let's say I don't get 7, I instead get 6. I am going to record it in my data table, and I'm going to complete steps 1 through 6 again until I get to 7. And notice, it says here, even if you get to 7, we want to see you do more trials in order to verify your results. So even if you get to 7, please repeat the same amount again to make sure that your data is reproducible. Okay? So to recap what this looks like, let's take a look at all of that together. So our first step, remember, was going to be to measure out about 100 milliliters of vinegar in our graduated cylinder. Our second step was going to then be to pour that vinegar into a mixing bowl. Our third step was going to be to measure out our baking soda as measured by teaspoons. Our fourth step, is going to be to dump that baking soda in with the vinegar. And then finally, we want to test our new solution and see, did we get a pH of 7? If so, do it again. If not, adjust the amount of baking soda to either be more or less depending on your pH. Okay, so after you get your 4 trials, 5 trials, 6 trials, however many it takes, you will then move on to the analysis questions. And the analysis questions are asking you to essentially analyze all of the information that you've recorded in your data table. So what was the original pH of your vinegar? Well, again, that's coming from our second column. What is the concentration of hydrogen ions for this pH value? Well, now we're going to have to start looking at some of our formulas. So remember, in order to get my hydrogen ion concentration, it is going to be equal to the antilog of our pH, right? So what we're going to do, the antilog of the negative pH, or the opposite pH. So we're going to take 10 raised to the opposite of our pH. Your pH values will differ, so you'll use whatever pH you've recorded for this question. For number 2, what was the final pH of your first trial solution? Well, this is coming again from the data table in the last column. So what is the concentration of hydrogen ions? Well, again, we're going to use our same formula, right? Our hydrogen ion concentration is equal to the antilog, or 10 raised to the opposite of our pH. So depending on your values, your answers will differ. Let's keep going through here, right? Number 3, were there more or less hydrogen ions in your vinegar or your neutralized solution? So this is essentially saying, compare numbers 1 and 2. Are they the same? Is one bigger? Is one different? Right? Explain then why you see those differences or why you see those similarities. Okay? Number 4 is a little bit of a deeper question, and again, I want to look at an image so that we can understand what's going on here. So first off, let's read the question. In order to completely neutralize your vinegar, what concentration of hydroxide ions from the baking soda would you need to add? So again, we have to understand that in our vinegar, we have hydrogen ions. So on the left here, I have our vinegar. I have it in a test tube. I have a bunch of hydrogen ions floating around. There's other stuff in there. There's acetate, and of course there's water. On the right side, I have our solid baking soda, and our baking soda in its solid form does not contain free-floating ions. It also doesn't contain the hydroxide ions, but to make this more visual for us, I've identified baking soda as having hydroxide ions. So let's see what happens when I mix the two together. Well, here I can see on the left I have 4 H pluses. On the right I can see I have 3 OH minuses. So what does that mean? Well, that means that one of my hydrogens and one of my hydroxides can come together to form water, and that gives us 2 hydroxides and 3 hydrogens. If we do it again, we'll get another water, and we'll get 1 hydroxide, and we'll have 2 hydrogen ions. And if we do it yet a third time, something interesting happens here. We run out of our hydroxide, but we have one extra hydrogen ion. So this would not be neutral, but instead it would be acidic. So in our question, what we're trying to figure out is essentially, how can I get my hydroxide ion concentration and hydrogen ion concentration to be the same so that I create a neutral saltwater solution? So again, that answer is going to vary based on your values, but this concept should help you to understand how to answer the question. Let's take a look at number 5. So number 5 reads, what would be the pOH of a solution with the hydroxide concentration that you solve for in number 4? Well, here we're solving for something different. pOH and pH are very similar. pH is talking about hydrogen ions, pOH is talking about hydroxide ions. How we solve for them is very similar. So what we are going to do is we are going to use our formula. pOH is equal to the opposite log of our hydroxide concentration. And again, your hydroxide concentration is coming from the answer that you've got in number 4. Okay? Last and final section here is our discussion. And again, this is going to be based on your results, based on your understanding. So all of this should come after we've done our calculations, after we've made it through the lab. And of course, if we still have remaining questions, reach out, get the help that we need. Okay? Have a great day, guys.